Welcome to Energy Effects in Binary Ionic Compounds. So, when we have an ionic compound, we have ions that pack together in a certain way. So this is the structure of sodium chloride, table salt. Now, we have alternating charges. We have some sodium ions, like this green one here, and each of those will pack in the crystal. And we have chloride ions, like these gold atoms here, and gold-colored atoms, not gold the element. And so each of these ions is bonded to other negatively charged. Each of the cations, the sodium ions, are bonded to some anions. But this sodium ion isn't only bound to that chloride ion, because there's nothing specifically important about this chloride ion. The sodium ion has a positive charge, the chloride ion has a negative charge. Well, if I put another chloride ion on this side, it's going to be attracted to the sodium ion too. And likewise, that sodium ion will be attracted to that chloride ion. And so we pack together our ions in such a way that each cation is surrounded by anions. In this case, it's 6 anions. And each anion is surrounded by 6 cations. And so we're not forming molecules, we're forming a lattice. It's sort of a grid structure, but it's a three-dimensional grid. And so we're forming this lattice, and we get some amount of energy out when we allow these ions to come together. So the change in energy that takes place when separated gaseous ions that are separated infinitely far apart, when those ions are packed together to form an ionic solid that looks something like this, we get some amount of energy out. So we have our positively charged cation in the gas state plus our negatively charged anion in the gas state. When we allow them to come together into a solid, then we get a lot of energy out, because we're letting these charges get very, very close together. They're no longer in the gas state. And so this energy that's being released in this reaction, or the energy is being released, and thus the change in energy is going to be a negative value. Right? So all of our lattice energies are going to be negative values. And they're going to be fairly substantial energies involved here. So let's look at an example reaction. If we want to find the lattice energy, it becomes very difficult for us to measure to measure this process directly, because it's very difficult for us to get a cloud of positively charged cations separated from a cloud of negatively charged anions, because they're going to be attracted to each other. And so what we end up doing to calculate this lattice energy is we look at some other processes. We do some other calculations first. So let's look at an example reaction. Let's look at the formation of solid lithium fluoride from its elements. So we start out with solid lithium and gaseous fluorine to form lithium fluoride solid. Now we can break this process down into 5 separate steps. The first step is the sublimation of solid lithium. So we take solid lithium and turn it into a gas. We sublime the lithium. So the energy of sublimation here is 161 kilojoules per mole. It requires energy to do that. Right? This is similar to the boiling process of going from a liquid to a gas, but now we're going from a solid to a gas, so it's going to take even more energy. The next step is the ionization of lithium atoms to form lithium ions. So we take our gaseous lithium atoms, we form gaseous lithium ions. So this is our first ionization energy of lithium, that's 520 kilojoules per mole. Again, it costs us energy to do that. We have to put in energy to pull those electrons out of the atom. So the next step is the dissociation of fluorine molecules. We take our fluorine molecules, split it apart into fluorine atoms. And the energy required to break this bond is 154 kilojoules per mole, but we only need to break half of the molecule, right? We need to break a full molecule apart, but we only need half of a mole to get half a mole of fluorine gas to give us 1 mole of fluorine atoms in the gas state. So We only need 77 kilojoules per mole of energy to break that bond. Next, we need to form fluoride ions. So we take our fluorine atoms in the gas state, add an electron, and now we get our fluorine ions. This is the electron affinity of fluorine, and this needs to be a negative value because every atom is going to give off energy, or the electron is going to give off energy as it falls into the potential well of that nucleus. So we have a negative 328 kilojoules per mole of energy. So if we get back 328 kilojoules per mole of energy. And the last step is the formation of solid lithium fluoride from our gaseous lithium and fluorine ions. So we have our ions turning into our solid there. And this is the lattice energy for lithium fluoride. So this is minus 1047 kilojoules per mole. So we can add all of these processes up. So I've listed out here those 5 processes that were on the last few slides. And I've listed out here the energies. When we add up all of these processes, we get our overall reaction going from solid lithium plus fluorine gas. That gives us the lithium fluoride solid. And we add up all of these energy changes, and that gives us minus 617 kilojoules per mole of energy. So this reaction will give us back 617 kilojoules per mole of energy. So even though we start out adding energy here, adding energy there, adding some more energy here, and then we get back some here, and we get back a lot there, overall we get out energy, which means that this reaction should be energetically favorable. We should end up forming lithium fluoride if we take solid lithium and gaseous fluorine and mix them together. And in fact, we do. We get quite a bit of energy out in this case. So we can show this graphically, what happens energetically as we go through this process. So we start out here with our solid lithium and gaseous fluorine. We have to add 161 kilojoules of energy to sublime our lithium. Then we have to ionize our lithium, and we have to add 520 kilojoules of energy. And then we have to add a little bit more energy as we break apart the fluorine molecule. And then we get back some energy as we ionize our fluorine atoms to fluorine ions. And then when we allow our lithium and fluorine to combine together, we end up way down here, we get a lot of energy out, and we end up here with lithium fluoride. And note now that this energy value is lower than where we started, at 617, or by 617 kilojoules of energy. So this lowering from where we started through the process, lowering down to there, that's that energy that we get out. Right? We have to put in some initial amount, and then we get some amount out, and that amount is more than what we had to put in. So overall, we release them. So this lattice energy can be calculated by a modified form of Coulomb's law, where we have our lattice energy is equal to now a constant K, which is different than the constant in Coulomb's law, times the same sort of quantity in parentheses that we had for Coulomb's law, so Q1 times Q2 over R, where K here is a proportionality constant that depends on the structure of the solid and electron configurations of the ions. So not all of the ionic solids have a structure that looks like the sodium chloride ones. So that K value depends on what the structure would look like and also the electron configurations of each of the ions. Q1 and Q2 are the charges on our ions, including the sign. And R is the distance between the center of the cations and the anions, so the distance from the center of this sphere to the center of that sphere, let's say. So note that the lattice energy is higher if the charges of the ions are higher. So as each of the Q values gets larger, then the lattice energy gets larger. And the lattice energy gets larger as our separation as R gets smaller. So as the separation between our ions becomes smaller, then the lattice energy gets larger. More energy gets given off if those charges are larger charges, or if those charges are closer together in the structure. So that was energy effects in binary ionic compounds.